at CMO in Spain, where he is the director since 2021. Carlos has also led the TJ2 stellarator team at CMO for many years. And he was one of the first experimentalists that actually looked into nonlinear turbulence flow interactions. He hardly needs an introduction amongst plasma physicists. And he has done work on Reynolds stress, flow generation, statistical properties of turbulence, much before anybody else was doing this type of work in toroidal devices. So with that, please take it away. The talk is called Transport Control and Self-Organization.
So thank you, Lothar. Of course, thank you very much for this kind invitation to be in this very unique meeting, which is the festival in Aix-en-Provence. Today, I will talk about transport control and self-organization. I have taken a few topics that are reflecting my own interest, but I think all of them are hot topics in the community. But before we go into, let's say, the essence of this contribution, I would like to make some tutorial statement about model validation, because at the end, this is a theory, a festival, let's say, dominated by theories, but are very good and very clever to have also quite many experimentalists attending. And then at the end, I will make a few remarks about something that maybe looks a bit out of the scope. And we should not forget that at least in the fusion community, our hope, our dream is to have energy. So at the end, even we do physics, very interesting physics, we should not forget that we need technology. And the issue of physics technology integration is one of the key elements for the future development of fusion. So let's talk about the art of the right approximation. Let me start making a reminder. Measure what is measurable and make measurable what is not so. This is a statement by Galileo by many centuries ago. And I think makes sense to remember in a theory festival where we have seen during the week many predictions coming from models, and in particular, yesterday, there was quite many statements about the possibility of having self-organization in fusion plasmas, what people call zone of flows. So theories made predictions about this self-organization. Yesterday, there was a statement about how fast particles, alphenic instabilities, might trigger self-organization in plasmas. There was some comments about isotopic effect, Lothar in D3D. So you might ask yourself, how is the radial scale of zone of flows scaling with the ion Lamont radius? Maybe it's one ingredient of the zonal of the isotope effect physics. So you have all these predictions coming from your well-developed models and theories. At the end, you need to measure somewhere to see whether your models are reflecting correctly reality. And remember that physics is an experimental science. So at the end, we need to confront both things. And to confront your predictions with experiment, you might need very complex systems. Systems that eventually are not in our hands, that should be developed. And so if this is the case, it might take a few years. Or maybe systems that are already in our hands. And then it is very good that this crosstalk between theorists and experimentalists is done properly to use what we already have in our hands. Because I took this example from previous talks about zone of flows, just to remind you that because zone of flows seems to be a reality, I don't have any doubt it's a reality at all, is now experimentally proved that they are real elements of fusion plasmas. We have built it in some experiments, at least in my home lab, a very unique diagnostic This is two accelerators, what we call helium beam, acceleration up to 200 kilo electron volts in one place. And you see there is another horn, a second one, 200 kilo electron volts. And we have two, and this is not a coincidence. And they are quite far away, as much as possible, because this was built during many years with a very significant effort in terms of budget and human factor to test whether thermal flows are real in the core of the plasma and to see the dynamics and properties. So here my tutorial message to the young generation of scientists sitting in this room, people that are doing the PhD or hoping to have a PhD, is that this crosstalk between theory predictions and experimental measurements might need time, and you should look where are these equipment. If they are not available, you should try to build a community, experimentalists and theorists, to build what is needed. My second tutorial statement is model validation as the art of the right approximation. Because we're using approximations. Theories are using many approximations. And we should be fully aware what are the limits. And also experimentalists, we are using plenty of approximations. Quite often, we measure in 1 point, or in 2, or in 3, but not everywhere. And this imposes some limitations in the interpretation. Let me give you an example. A well-known approximation. Magnetic flux surfaces are potential in magnetic fusion devices. That's something that I assume as granted 10 years ago myself, because the particle dynamic is very fast. In 2013, I was visiting IPP Greifswald, and I have an informal cup of tea with the head of the theory group, Per Helander. And then in 2013, he told me, we are doing now very fancy simulations to verify and to see how close to equipotential are magnetic flux surfaces in accelerators. And we think this is a very important topic. That's what Per Helander told me, because we think that if they are not equipotential, they might have a strong impact in impurity transport. And impurity transport is a very hot topic everywhere, in particular in accelerator. Then the conclusion from this informal talk was that the validity of this approximation might depend on where you are. If you are in a tokamak, if you are in accelerator, and also on collisionality. When I was back to my home lab, we discussed this topic because it's not trivial to see whether magnetic flux surfaces are equipotential if you keep in mind the input from simulations. The departure from equipotential values might be tens of volts. It took 2 years to build an experiment, 2015, and to convince ourselves as an experimentalist that Per Helander team was completely right. Magnetic flux surfaces are not always equipotential. It depends on the scenario. Later on in the last 2 or 3 years, we did a much more detailed development in terms of comparison between models and experiments. Now we know that if you measure the radial electric field, because magnetic flux surfaces are not necessarily equipotential, the radial electric field in one location might be different to the radial electric field in another polar position. And this is now an experimental fact. And now we know that the level of agreement between predictions and experiment is qualitatively fine. If you go into the details, there are issues still under discussion. But I think it shows how the right approximation is important. And once you have this communication between theories and experimentalists, you build a test and using the time scale. The discussion with a cup of tea, Greifswald 2013. First experiment 2015, which is not bad. 2 years is quite short. More details, more than 5 years. This is the time scale you have to keep in mind. I'm referring to the young generation. Be patient if you want to test something coming from theory. The art of the right approximation. I will not explain you my life, but I'm pretty sure all senior scientists sitting in this room, if you ask you how successful were your ideas, I think the truth is I have been most of the time unsuccessful. This is just the reality. And eventually, yes, we did something that we believe is useful. So my comment to the younger generation as a tutorial statement is that be ready for what people call unsuccessful experiments. But in reality, I don't like this word because with unsuccessful experiments, you learn a lot. And quite often, I will argue that the disagreement between models and measurements has been historically the trigger of great discoveries and new physics. I will not go into many details, but I just want to mention one example that I know quite well. In JET, during the DT scenario development, there was in JET tokamak, there was a great effort to measure and to validate temperature profiles. There was a great effort to compare two systems in operation, Thomson scattering and EC. And you might be, for sure, my senior colleagues, they know that there was a historical disagreement between these two diagnostics. And the disagreement was not small, it was in the core in up to 2 kilo electron volts. This was quite significant. Maybe you know that experimentalists, like myself, we don't trust our own measurements. And that's why we have a tendency to compare with other systems. Because we know the details. So we know how difficult it is to measure something. So you always get doubts about instrumental effects. So during this disagreement between Thomson and ECA, of course, Thomson people from JET thought it's my fault. And ECE people thought it's mine. In reality, both were correct. A model distribution function analysis obtained by fitting the ECE spectrum reveals that there is a distortion from the Maxwellian. So the conclusion was that this, as a consequence of the distortion of the Maxwellian distribution, and the temperature that you measure with Thomson should be lower than the temperature measured with ECE. So this is an example of disagreement that took many years to find a solution that was a kind of discovery, non-Maxwellian distribution. So having said these 3 tutorial statements, if you want to measure something, talk to experimentalists, keep in mind the time scale, look about what is available, contact these guys and try to convince and to have a team. Be ready for unsuccessful experiments that are not unsuccessful, are always very useful. Last but not least, try to emphasize always what are the approximations, assumptions under your models as well under the experimental side. Let me say something now about the topics I have selected by personal interest that I hope are also your own interest. In the first topic, I will discuss 2 questions that seems to be extremely far away. Why decoupling between particle and energy transport? This is a very fundamental question because ideally, if you want to develop an ideal a scenario for a reactor, eventually you want to decouple particle and energy transfer. So you want to know why eventually these channels are decoupled. And the second question that you might think, what is the connection? Core plasma fueling. To fuel the core of our reactor is a tremendous challenge that in reality we don't know how it's going to work. Of course, having core fueling in existing devices is easy, but now we should think also about the future reactor. So what is the role of positive and negative density gradients to allow us to have core plasma fueling? These are the two questions that put together, because you will see that there are some strong similarity. If we talk about decoupling between energy and particle transfer, I took just one example. I will not go into any detail. And the example is coming from MIT, the so-called I mode, where they have clearly proved that when you go in this transition from the L mode in green to the I mode in purple, you see that the density profiles essentially remain the same, but the big change is in the temperature profiles. So just looking into the profile, you conclude that there is a decoupling between particle transport and energy transport. And of course, the question is why we have this decoupling. And for sure, the answer is not just one answer. There are different possibilities. But today, because this is a tutorial talk, I will not go into all the options. I take one. Maybe the most trivial explanation is that if you look at the particle transport and the energy transfer driven by turbulence, in the case of Alcator, anomalous transfer is the dominant one. You see you have different contributions. If we talk about electrostatic turbulent transfer, you have this very well-known term, the correlation between electric fields and density fluctuations. And if you look now in the energy flux driven by turbulence, you have also the quadratic term involving the electric field fluctuations and the temperature fluctuations. So you have a strong decoupling between particle and energy transfer. One of the possibilities, I will say the most trivial, will be what happens with the crossface between density and temperature fluctuations when you have I mode regimes. So this is the key question I will put today on the table for the issue of the coupling between energy and particle transfer. Now let's talk about core fueling. As I said before, having core fueling in JET tokamak, in West tokamak, in ASDEX, in D3D is not difficult. You just use pellets and you have good enough penetration in general. But having core fueling in ITER, and even worse, in demo, is a fantastic challenge because all the pellet ablation will happen very close to the closed flux surface. And then once you have the pellets and you have the pellet ablation, you will get a negative and a positive density gradient. And then your hope is that right here, you will get inward transfer, pushing particles to the core. So how to get inward particle transfer? Again, if you believe that turbulent transfer is going to play a role, I go to the same expressions, and then for the particle transfer, we have the cross correlation between electric fields fluctuations and density fluctuations. So you want to have inward particle transport, you have to deal with the phase relation between density and electric field fluctuations. So you see how two fully independent, fully far, very fundamental questions, the decoupling between particle and energy transport and core Fooling has something in common. Is the physics of cross phase involving density, temperature, and electric field fluctuations. So the challenge, the open challenge today for the young generation, the physics of cross phase and the physics of cross validation of cross phases. Well, this is a fascinating topic that maybe will deserve in the next festival and a specific session, so everybody can learn the details. And of course, I will be very happy, this is included, to join the meeting as a senior student to understand the details of cross phase. So I will not go now into many details. Here we go into the, is the power dynamics physics, what really matters for the cross phase. We have to consider electron-ion collisions, wave-particle interaction, the interaction between passive trapped particles, the role of electric fields, shear flows. Eventually, we are in the very far edge, we have neutrals. And now we know, 2022, that neutrals are also reacting to plasma turbulence. So eventually also neutrals in the very far edge might play a role. So plenty of open issues for young scientists attending this meeting. I will not go into many details. I just take one example. And I take the example that hasn't been mentioned yesterday many times, and possibly also last week many times. It's the question of E cross B shear flows. We have learned yesterday, and for sure the day before, that E cross B shear flows can induce energy redistribution. So the reduction of the size of eddies and so on. And this is affecting transport. But also E cross B shear flows can affect the cross phase. It is very interesting. I will not try to do now any bibliographical analysis because putting in one biograph a work during 30 years is not trivial. So if you don't see your reference here, don't be offended. It's because I wanted to put the whole story in one biograph. So I try to see how versus time the story of E cross B shear flows, cross phase and transport has been evolving. The topic of E cross B shear flows and transport, the starting point is the beginning 1990. And then I didn't have space to put all the reference. So a huge number of papers has been looking how electric fields are affecting the level of turbulence and transport. If you look at the story from the perspective of cross phase, it's interesting because there is a gap. Looks like, again, don't be offended. Maybe you thought about this topic in 1992, but you look in general numbers, I think you have to wait almost 10 years to see. This is an interesting paper, a paper by Boedo et al., where they were doing experiments in Texas, doing biasing, and they observed that with electric fields, eventually in some scenarios, the reduction in the level of turbulence was quite small. The true change was in the cross phase. It was a kind of surprise. It's nice to see this paper because even the experimentalists are surprised with the result. And then the paper by Terry et al., where specifically they are looking into the E cross B shear flows and cross phase. And then again, without going into many details, if you are not in the list, don't be offended. I just wanted to show that since then, there's a quite significant number of activity looking into the cross phase and the role of electric fields. Many of this work is done in low temperature plasmas, simply because it is much easier to develop techniques to measure the cross phase. But there is also a very important ongoing activity. For instance, in Aztec's upgrade, since a few years ago, they tried to develop systems involving cross ECE diagnostic and reflectometry to measure in the same location the cross phase between density and temperature fluctuations. Also, just to mention recent development, in my home lab, we have developed very recently, 2022, triple bundle experiments that allows us today to have a 2D mapping of density and temperature fluctuation. And I hope these new tools will help a lot to disentangle the story of transport decoupling and phase between density and temperature fluctuation. Just one example of cross phase. I took one example. Also, I take many examples from my home lab just because it's easier and I know very well the details. And this is an experiment in TG2 experiment where we are looking alphenic activity, alphen modes. And we try to measure, and actually we have measured the E cross B transfer driven by alphenic modes. We are able to characterize density fluctuation. You have these alphenic brands, potential fluctuation. You see the intensity of the brands is not the same for density and potential. And also you see the alphenic brands in magnetic fluctuations. Again, the magnetic fingerprint is not necessarily equal to the fingerprint in density and potential fluctuations. And in the bottom, you can see the E cross B turbulent transfer driven by this alphenic activity. And you can see that some alphenic brands, they have outward transfer. Other branches, they have inward transfer. Why? We don't really know. Very recently, in my home lab, we did experiments with alphenic activity with counter MBI, just because we thought, well, power dynamics is the key ingredient for cross phase. What happens if we do co-counter? The surprise is that using our present database, the inward, outward transfer might be connected with the co-counter MBI. But this is so fresh and so new that I just want to give you this message, that this is a very active area and that the cross phase determine inward outward transfer, that the inward transfer is what we dream to have in a reactor for fueling. And if we don't get it, we have a problem. Phase physics is not only a very basic science, what it is. Very beautiful. I would say is a pragmatic question, like fueling. And again, in the area of fueling, I just want to mention that yes, we try to produce experimentally hollow profiles. That's the profile we will have in our reactor. Remember, ITER and demo. And then we try to see in the hollow profile what happened at both sides of the hill. Ideally, we want to measure E cross B transfer, the cross phase. Remember, in this case, cross phase between density and electric field. We are not yet. It's a bit tricky. I will not go into any detail. But today, we are able to measure the level of turbulence in density fluctuations at both sides of the hill. This is one scenario, also in my home lab, where we have a negative positive density gradients And you see, you have turbulence at both sides of the hill. In this particular case, where we are supposed to be dominated by TEM instabilities, most of the turbulence is in the negative. But you look into the positive gradient, we also have in fluctuations and some coherent modes. How these fluctuations and coherent modes are affecting into the crossface today is a fully unknown question from the experimental perspective. Of course, there are simulations, genetic simulations that emphasize the role of collisionality, but the validation still is a very open question. And I put here on the left just the raw data underlying these profiles, because now experimentalist is amazing what we have developed in the last 20 years. I measured during many years, we measured 1 point. Then we measured 2, 3. Now we get a 2D view, which is amazing. What we have learned after 20, 30 years of improving our diagnostic capabilities. This is a 2D view of plasma potential in our home device. It's quite significant, and now we try to expand our measurements to the top and to the bottom to have the whole cross-section. Still is not in our hands, but hopefully in the coming years should be. Soil width and spreading. Well, this is a topic I know has been discussed many times during the festival. Again, don't be offended if your name is not in the list. I just want to remind that this is a long story, in beginning 90s, almost 30 years, that the idea that electric fields can affect spreading is nothing new. I think this war mid 2000 is one of the first that shows how electric fields are affecting the spreading. Also, we have seen nice experiments how spreading might be also connected with magnetic topology. And now in the last few years, I didn't put any reference because there are quite many, the issue of spreading and power exhaust is a very hot topic, because at the end, we are supposed to be unstable region that here I am assuming this is the DX stable region that I will assume is the scrape of layer. And then in the middle, we have an electric field. And many theoretical work has emphasized that the connection between the unstable and stable X scrape of layer might be controlled by the radial electric field. So based on all these theoretical development, we have developed, again, in my home lab, a very focused program, extremely focused. Answer this question. Do we have propagation of turbulence from the edge into the scrape of layer? And if yes, what happened in this propagation when you modify the radial electric field? This sounds very easy, but it's a very simple question. You just need to measure turbulence in the edge, turbulence in the scrape of layer, and to modify the electric field. Sounds easy, but it's a tremendous challenge, because if you want to measure spreading, you have to measure at the same time in the edge and in the scrape of layer. So you don't need one sensor, not two. You need minimum 10, 20 working at the same time. And then you need a knob to modify the electric field. And that's not trivial. How to modify the electric field? In tokamaks, yes, you can go L mode, H mode. It's a possibility. But you have only two values. Ideally, you would like to have positive electric field, zero electric field, negative electric field. And ideally, you would like to do this modification very slowly as you wish. Is it possible? Yes. Where? Not in tokamaks, in stereometers. And then I will show, again, without going into detail, this was the PhD of Gustavo Grenfell, now in IPP Garden, where we did two experiments. Two, because remember, experimentalists, we don't really trust all our measurements, but we want to have two strategies to see that the results are consistent. So first strategy, very simple, put an external knob, biasing to on, off, and to change the magnitude of the radioelectric field. And this is a strategy describing this figure. It looks very nice. So you might think it's a simulation. It's not. It's an experiment with more than 15 sensors working simultaneously in the scrape-off layer and in the So what we do with biasing, we change this, and this is always red. And in the X, where we apply the electric field, we can deepen. In the bottom is the most important figure. This is the E cross B turbulent transfer. So you can see that you have transfer in the X, and you see you have also transfer in the scrape-off layer when the electric field is very weak. So this yellow means very small negative radioelectric field, less than 1 kilovolt per meter, which is very, very small. And then blue means that we get here electric fields in the order of few kilovolts per meter, quite significant. And then you can see turbulence is reduced when you apply electric fields in the X, but also in the X and the scrape-off layer. And on again, the strong electric turbulence is out both edge and scrape-off layer. So I think this is an example of a very tricky experiment. It's not done in one day, but very visual, because you can see that without any interpretation, you can see that yes, edge and scrape-off layer are connected. But if you want to look into a different strategy.
On that exact result, have you tried not to do it in a correlated way, but in a smoothly varying way? Because there you can always argue that the very rapid change of ER is somewhat driving a change in the turbulence itself or on the instability itself. So possibly a bit hard to conclude on the calculation from core to edge, from edge to solid.
Now, this is a very good question, a question that we did ask ourselves in a few years ago, and that's why we did a second experiment. In the second experiment, we modify, as you say, the electric fields very smoothly, without any biasing. So this is a very unique property of accelerators, where you know that the electric field, the mean radial electric field is connected with neoclassical mechanism, at least partially. And then you can change the radial electric field as slow as you wish, from positive through 0 and negative. As small as you wish is using the control knob, which is the plasma density. So what we do, we ramp the density very, very slowly. And then in time scales of tens of milliseconds, the electric field is evolving. And that's what we did. And so in this experiment, we are ramping the density from 5, 10 to the 19 meter minus 3, up to, in this particular case, up to 8, 10 to the 19, and then the density goes back. In this, the critical density where the electric field goes from positive to negative is somewhere here, 0.6. So in this region, the electric field is positive, is what people call in accelerator community the electron root. And then we have all our sensors, 15 sensors measuring edge and scrape-off layer. And then we look how information that is triggered in the edge is propagating to the scrape-off layer. This is done using transfer entropy analysis, but I will not go into detail. But you can see that with the density now is high enough, the electric field is negative. And then the information that is triggered in the X essentially remains in the X. And then when you are back into the positive by the electric field, information that is produced in the X is propagating very deep into the scraper flame. So this is a different strategy. Of course, in this case, it's just one example, but we can ramp in 100 milliseconds or 200 milliseconds. This is a full control as one of the characteristics.
Isn't it important in part of this story to validate these indirect measurements with a direct measurement of the flux of turbulence energy through the separatrix? I mean, you know, particularly your spiel on cross phases and all, it applies equally to that, right? And I mean, that becomes part of the story. And that's rarely done, as you know.
Yeah, I think that for the energy flux is more difficult because you need to measure the temperature fluctuations, right? And this is order of magnitude much more difficult. Remember, for this experiment, we measure turbulent transport in many different locations. So you need a multi-point measurement. This is feasible for density, for particle transport, for density and electric field. I will not say it's impossible, but it will be a tremendous effort.
You can measure the kinetic and the flux of kinetic energy, certainly, because that's basically for E cross B, that's potential. And you can measure in the level of simple drift wave, the internal energy. I mean, again, you're stuck with an approximation, but you still get some direct information.
Yeah, I fully agree. I thought you were referring to thermal.
No, turbulence energy.
Turbulent, yes.
Spreading is a flux of turbulence energy.
We could, let's say, recompute this database to compute the B tilde square term, which is somehow connected with the, or N tilde square, which is the kinetic. Yes, it's a good point. Yes, this
So that's what Ting is doing.
Yeah,
right?
yes. This is what Sendu has been doing. So my conclusion is that we talk about many open questions. Is spreading controlled by electric fields? Yes. And today I think I refer to experiment in my whole lab just because I know all the details. But as Pat mentioned, this has been also done in other experiments. I think this is a clear example of how a theoretical prediction has been validated, at least qualitatively validated in many different experiments. Fast particle stabilization. Well, I think this has been mentioned yesterday. There was a specific contribution where the question of self-organization of fast particle was addressed. And I think that this is indeed a very, a bit late, isn't it? Yes.
No. We had about 7 minutes today.
Okay, I will try to move a bit faster, or maybe just skip some elements. But the fast particle, I think, is so fundamental because at the end, a reactor will be fully dominated by fast particle dynamics. The story in a cartoon is simple but complex. Fast particles drive alphenic activity. Then you have a nonlinear mechanism connecting alphenic and turbulence. You get zonal flows, zonal fields that eventually is regulating thermal transport or the nonlinear saturation of alphenic instabilities. Again, this is a very interesting topic in terms of bibliographic analysis. The story of zonal flows and turbulence driven by turbulence is something that has been done since many beginning 1990. The story of fast particles and zonal structures, there is a gap. Again, it's interesting. A gap of almost 10, 20 years And then from this point, again, if your reference is not included, don't be offended. I just wanted to give you a visual analysis of bibliography. Now the story is dominated by theory, mainly simulations, ton of fields, ton of flows. Validation is, I will say, for the young generation, fully unexplored territory. And almost fully unexplored territory. There are two strategies here. One is to look the nonlinear interplay between alphenic activity and low frequency modes, sonor flows. Do we have any evidence of nonlinear coupling? That's something that was also, there were some questions in this area in the session in the morning. And the second strategy will be, is there any direct relation between fast particle driven modes and sonor flows? For the first question, the answer is yes. There is a very clear experimental evidence that in some conditions, we have a clear nonlinear coupling quantified by coherence between alphenic branches and very, very low frequency modes. This was done quite many years ago. Also, sorry, I refer always to my whole lab. Don't be offended, it's because I know very well the details. This is just an example to illustrate that this nonlinear coupling is an experimental fact. It has been observed in specific scenarios, not all of them, because it's not so trivial. Once you move into a regime where you only have very low frequency sonor flows, this nonlinear analysis is not trivial. And the second strategy to address the question of fast particles, alphenic mode, is a strategy which I think is very complex. This is the truth. What we are doing is using two heavier beams at the same time to relocate the heavier beam one in one point. We strip the heavier beam number two around, and we look for long range correlation. And this is the way we are doing now in Madrid. I will not go into many details. I just wanted to say that, do we have sonor flows in the core of accelerator? Yes. Sonor flows are everywhere, but the amplitude depends on the scenario. This is an example of measurements in row 0.3. This is the long range correlation in NBA plasmas. And you can see the long range correlation in density is very weak, not zero, but weak. And the long range correlation is huge for very low frequencies. This is the fingerprint of sonor flows. I will not go into many details. Of course, we have also long range correlation at the alphenic activity. Because time goes by, I will make a long story an open story short. Yes, we have sonor flows in NBI plasmas with alphenic activity. Are these sonor flows triggered by fast particles? The answer is we don't know. This is the truth. And I think this is very fundamental question where we all together, strong effort in theory, and also now with our diagnostic capabilities, we should try to address experimentally. About neoclassical turbulent transport, just one remark. This is a topic that has been discussed by many colleagues sitting in this room. Yes, the coupling, there are many reasons to explain why neoclassical radioelectric fields are also connected with sonor flows. I will not go into all the possibilities. Some experts are in this room and can go into many details. One is very obvious, is the role of electric fields, neoclassical radioelectric fields, to break the symmetry and then to drive Reynolds, electrostatic or diamagnetic Reynolds. And also electric fields are affecting particle orbits. And this is a story of sonor flows. Here, the only comment for the young generation of scientists that if you plan to do gyrokinetic simulation of sonor flows, I would argue as an experimentalist that please don't forget to include in your simulation the neoclassical radioelectric field. Otherwise, you are missing something very, very crucial. And as far as I know, this is still not so trivial in all simulations. Do we have any experimental proof that these electric fields are connected? And the answer is yes, capital letters. There is no doubt. Both electric fields are connected, but the details are still under discussion. So, but I know I am a bit late, but I cannot resist to make one comment about physics and technology, because although this is a theory festival, at least part of myself, part of this community, our driving force is to have energy. So it is very great that we look into a fusion reactor from the point of view of plasma physics, energy confinement, heat power loads, core fueling, impurity transfer, and in particular, these unique impurities that are produced in a reactor, helium. But we should not forget that in addition to the plasma physics, for a reactor, we have technology. So we have to remember that we will need some boundary conditions to have tritium cell sufficiency, that we will need a scenario where materials are okay for the string condition that we will have in a reactor. We should not forget that we should think about the cost. Remote handling. Remote handling is very, very crucial, because if you build a fantastic, let's say, accelerator with a fantastic confinement time, and you don't have enough space for remote handling, then you do a fantastic plasma physics experiment that might be fully irrelevant for a reactor. You should not forget these boundary conditions, and of course, social acceptability, because at the end, fusion is a nuclear energy. So my last comment is that when we talk about validation of models, and I have emphasized the experiment, the models, the comparison between theory and experiments, and I go through some, in my view, key areas where we still have plenty of things to be done, fast particle dynamics, or heat loads, or reactor fueling. We should not forget that we need one more branch, which is the technology. And at the end, we should do this validation in the scenarios, if possible, that are considered reactor relevant. So as a final conclusion, now that we are living a very dramatic situation all over the world, and particularly in Europe, where this situation might be also an opportunity to push for nuclear fusion. We should not forget that we should try to accelerate fusion, and to accelerate fusion means we need the integration of validated physics and technology, both together. And that's it. Sorry, the chair, for being a bit late.
You're doing okay.
Oh, yeah.
Thanks for this excellent overview, Carlos, and we are ready for questions from the audience. Anybody wants to start?
Just Mr. Lareto, in principle, you have more room when you talk about to control the electric field, the magnetic configuration, at least that's my view. So what is the status for sensitivity about that? What is your experience?
Yes, you're completely right. We have much flexibility to play with electric fields and in tokamaks. In tokamaks, you are always, or we are always, because we are also working in tokamaks, in the iron route, so negative radial electric field. In accelerator, we can play using the classical mechanism. So I will say that in TG2, our flexibility is very well developed in terms of the scenario. We can play with electric field as we wish. We know how to do it because we have all the expertise. The prediction from neoclassical models to give a qualitative description of electric field is very well done. It doesn't mean that the electric field is only neoclassical, but at least in the first approximation, when neoclassical models predict positive electric field, we get positive. When they predict negative, we get negative. Then when you look into quantitative comparison, we have a disagreement. And the disagreement, we believe, is due to other mechanisms, including turbulence, like in tokamaks. But this tool, not only in our whole lab, but in all accelerator, is something that is something of great, might be the great interest for the tokamak. And concerning tools, you see, as in the beginning, we thought that we should have extremely advanced diagnostics for electric field. And I think that I didn't go into all the details. I just emphasized one because the effort to have a dual helium beam is tremendous in terms of budget and money. Now the system is working very well. Actually, because I mentioned now the helium beam, of course, you might know that this system has been developed in FIAMAT in very close collaboration with Kurchatov Institute in Russia and Kharkov Institute in Ukraine. And so it's amazing to think that we have a joint lands, Kurchatov, Kharkov, FIAMAT, November 2021, with a toast for prosperity and long-standing collaboration. Then we have February 26th, and we have now, we contact our colleagues from Kharkov because the situation was very, very difficult. And then I am very proud of the reaction of FIAMAT because in two weeks, beginning March, we have 2 scientists from Hidalgo and the whole family in Madrid. They are now working with us. The interaction, so they are running the whole system together with our staff. The interaction with Russia is, as you know, without going into many details, is postponed following the rules. We hope that the interaction with Russia will be back to our home lab as soon as possible. So yes, going back to the physics question, we have a very, very unique diagnostics that allows us questions like alphenic activity and self-organization, spreading, and whatever you do. So my message will be for the young generation, but also for the senior scientists like you, that you have a specific prediction from the model, that you need something very unique. Of course, utility is having fantastic tools, but you might also put on your agenda not only tokamaks, but accelerator.
Another question, yeah.
And then during your talk, you had a very optimistic point of view about the attitude of experimentalists with respect to their own diagnosis. Very often, I could see another attitude, which is more like the 6 blind men and the elephant, where each person convinced that he or her own measurement is the right one, and it's difficult to get to validate the database for the various discharges in the machine. So this was the negative part of my comment. But then there is possibly a positive one. I think the development of Bayesian approach might already enable more collaboration between people, because there is no longer the right diagnostic, but there is this idea that let us collaborate, let us use Bayesian approach or the holistic approach, and let us try to extract the maximum of information from our data.
Yeah, well, of course, your experience, mine based on many years of experimental physics is that my statement, I think, is reflecting the majority. I think experimentalists doubt a lot about their own measurements. At least this is my perception. And theories in general, they have something that I admire a lot. They are very self-confident in the sense that you talk with a theorist, and then it looks like that they are completely sure the theory is correct. So for me, this is very interesting. And we might talk about sociology or sciences. Of course, there are many exceptions, but I think this is, in my view, this is a rule. And then from this perspective, I think this collaboration is very interesting, because then experimentalists get some self-confidence. If this guy believes his theory is right, I should also believe my measurements are correct. And I hope that also the theorists think, oh, these guys have made so many doubts, maybe I should think that maybe my theory might be not a bit correct. So I think this is, for me, has been also very interesting, this interaction with theories. Without going into details, I think in general, from the probabilistic view, I think, at least based on my database, this is the technique.
But in fact, when people are stating that they have just to follow that, when people are saying they are measuring the temperature, as you mentioned, in fact, they are measuring something they interpret as a temperature. And in some moment, there is a dissymmetry in the Maxwellian, and so you have two diagnostics which are right. All right, it will not be the same temperature. So I think this is a difficulty. But there is never a pure measurement of the temperature of any quantity. There is a theory behind. And the Bayesian approach, what is interesting, it forces people to really take into account seriously of the theory which is behind the measurement.
Yeah, so I had kind of two related questions, both on electric fields. Could you give us a critical appraisal on what's actually done, or usually, which is to calculate the electric field by radial force balance? Right, that's, so then the question is, when you have a direct measurement, and particularly maybe in Stellarator as well as tokamak, well, how good is this approach to business?
Well, I think this is a very good question, because, of course, in Stellarator, we try, as tokamak did before, how to construct the radioelectric field from the pressure gradients and toroidal velocity. The conclusion from more than one accelerator, I think the first one was Bellington 7X in graphene. They saw very clearly that the electric field in accelerator is not necessarily dominated by the pressure gradient. This was a clear statement from this 200 review of Bellington 7X. Also, we did this exercise in TG2, and we also concluded that the pressure gradient is not a dominant player of the electric fields. That's why when I say that we use the classical physics to give a positive electric field, let's see what is the neoclassical. Negative, let's see what is saying neoclassical. It doesn't mean that the whole story is neoclassical, but qualitatively help you to define the scenarios. But when you go into the details, there's a clear disagreement. I know that in some tokamaks with very good confinement, like ASICs, they claim that the electric field is fully dominated. The radioelectric field is not fully dominated by pressure gradient. In the case of accelerator, this is not necessarily.
But in the edge, right?
In
the
the
core, when you have momentum, beams and so on.
Yeah.
This is still neoclassical, but it's not pressure gradient.
Yes. I think this really helps on how the NBI can be eventually controlled.
So in this begs then the other question that always sits in my mind is, if we really understand the radioelectric field, or we think we do, as should be able to calculate it correctly for reverse field pinch. And And in particular, let's forget the QSH and such things, even the normal operation, which I think becomes an interesting challenge because you're dealing with a stochastic magnetic field globally and an electron-dominated system. And if you really know what's going on, you should be able to get all three of the devices right. But I never even see the electric field in the stellar in the RFP addressed, with the exception of some stuff from Wei Xing Ding, right, on the MST some years ago. And you have a comment on, I mean, you were many years ago, you and Benjamin were off leading, multiple comparisons of things.
Actually, I have, I don't know whether with my colleague from Padova is sitting in the room now. Oh, yes, it's here. Actually, yesterday we have a very interesting discussion to put together RFPs and tokamaks and accelerators in a topic that I believe you like very much, is the question of density limit. How magnetic topology models coming from RFP about density limit could be eventually also tested in the accelerator, but we have also the capability to have a very well-defined magnetic areas in the periphery. So I could agree that this interaction with the three pillars should be further emphasized. And maybe if I take one topic, probably the issue of electric field and density limit, because you know very well, electric fields and sonar flows and blah, blah, blah. Maybe a good topic for further interaction with the electric fields, sonar flows, and density limit. And of course, here we have very expert in this topic. I don't know whether they want to address.
I had a connected question, because you have varying regions of favorable, unfavorable curvature. Is there a way to arrange the equilibrium in a way that the two heavy beam probes can look at favorable, unfavorable curvature regions at the same time? I mean, it's not clear that we would see a difference because the connection length may be too short, but have you thought about that or tried?
Yes, actually, we have a proposal. The main author is Daniel Carralero, has been working many years in aspects. And the idea is to look at how magnetic curvature is affecting blood dynamics. And this is a point, again, where accelerator can do something very unique. Because in accelerator, we have regions with different magnetic curvature. So in the same shot, we can test all these models based on magnetic curvature. These areas has been identified. For the Kelvin beam, it's going to be a bit difficult because of the spatial resolution. So we will use other techniques. So yes, this is one area which is fully identified, and these experiments are in the queue. As usual, in a program, you have a specific number of days, and you have a long queue. And this experiment is just very close to the beginning to jump into the next experimental campaign. That is a very good thing.
Do we have still time, or do we need to break because of the 4 p.m. coffee break? Or
If there is a pressing question, then
any?
Regarding the biasing experiment, when you switched it on and off, so you're seeing that the transport in straight form increases and so on. Might there be a way to disentangle between locally driven turbulence in the spirit of Potts Hope and what is spread? That's the first point. And the second point, what about the ratio of the lambda Q in the scrape off? In those two cases, and maybe related to the cost in terms of energy budget that you have to put into polarized system.
Concerning the first point, our strategy has been to use the transfer of information to quantify how energy, let's say, is propagating. I know it's not the same, but it has been the way we did so far. But it's not the only way. So,
But this analysis does not take into account the linear term that would be able to drive locally.
this technique only tells you how much information in terms of bits is propagating randomly. It's difficult to quantify, that's why it's very basic, but it was enough to convince ourselves that we have a spreading of information, understood it that way. We have a spreading of information from the edge into the spread of data. But following also Pat's remark, yes, we can try to do different analysis looking into how the kinetic energy of turbulence is propagating radially outward. Also, another point that we have also discussed is our idea when we did this experiment. We thought that the natural way is to look propagation from X into the scrape of layer. Now, based on recent developments, we plan to do at very high densities, very close to the density limit, to see whether there is any evidence or not of propagation of information from the scrape of layer into the plasma X. And this is also we did some experiments. I don't want to say anything now. We plan further experiments in the next campaign. So yes, there are plenty of activities for the spreading of information. That's what we did so far, and to look into the propagation outward and inward, particularly in the density limit, is in our plans for the next campaign. And concerning the issue of biasing, of course, biasing is a very, that's why I mentioned that we try to have two different strategies. Because biasing is very good because it's something that you can change, it's very visual, blah, blah, blah. So it gives you the first interpretation. But you pay a price because also biasing might impact the clean interpretation. That's why we did this very slow ramping experiment for the electric field without any biasing, and the results are fully consistent. So my conclusion based on this similarity of these scenarios is that biasing is not affecting the interpretation of spreading of information.
And what is the follow-up of
and then, yes, it's a good point. The tail in the density is moving up and down together with the spreading. So far, we only look into the density, not in the temperature, just for instrumental vision. So yes, when you have a spreading of turbulence from the edge into the scrape of layer, the tail in the density in the scrape of layer is moving up. And when the spreading is reduced, it's moving up.
How are you performing the biasing experimentally?
Experimentally, in this particular, there are two ways. One is to do the biasing with respect to the vacuum chamber, or we can do biasing.
You mean you bias locally the chamber?
No, we bias it's an electrode.
Okay.
It's a standard technique. You put an electrode in the edge, and then you can bias with respect to the vacuum chamber, or you can bias with respect to another big limiter. These two options are feasible. In this particular case, the experiment was done with an electrode in the edge and the limiter in the scrape of layer. So we just trigger an electric field between the scrape of layer and the edge. But this is the standard technique that has been used since 30 years ago.
Or the H-bodies, bias H-bodies, atomic H-bodies. Of course, you get line time, and you get some effect of the line time. The sheet is partially reduced that can also potentially affect your turbulence drive.
There's a question or comment that comes from what you just said. The transfer entropy method is an interesting method, but I think one must be very careful into which quantities it's applied to, because it's a bivariate method, whereas the flux of the spreading is a triplet. So on what quantities did you apply the transfer entropy? Because you have 2 time series, you apply that method, whereas as you mentioned yourself, you can have 4 spaces, etc. between the triplets.
Yeah, in this basic experiment, we did this transfer entropy in the most simple quantity. We were the floating entropy because it's not easier to measure. But but you're completely right. So for this conclusion, is a transfer is a propagation of information in potential. We don't have data for density just because it's a bit more complex. But I think this technique that has been actually developed by one of our colleagues, in communism, is very interesting. Today in the morning we talk about this in the coffee break about how to compute energy transfer between different scales. We tried many times using biocoherence and we failed, or at least we failed. I was not convinced that I can trust because of error bars. So maybe this transfer entropy could be a way. If you talk about arsenic activity and some of those, this might be an strategy. It's not the energy transfer, it's a transfer of information. But we are seeing a point where we want to see how a specific NSD alpha activity is propagating information into the low frequency zone of flow. That's something that we see in our agenda to look our experimental data, because the standard biocoherence, it works very well. You have very coherent modes because the statistic is limited. So with 2 clear alphanic modes and very low frequency modes, coherent, you can detect this nonlinear triplet coupling. But once you go to very low frequency zone of flows that are not necessarily quasi-coherent, this technique doesn't work, or at least doesn't work. Gives you nothing, or we see error bars. So I think we should think about this technique to be applied.
I quite agree that it's an interesting technique, and following the work of Van Milligan, we applied it ourselves. So, but I'm just saying that what you would probably like to do is the transfer of an n tilde and phi tilde square, or t tilde phi tilde square, which is probably extremely difficult, and that may give a quite different result from just apply to phi tilde. That's why I'm asking.
I agree, it's something to be done. So far, this was beyond our capabilities, because for the spreading, you need to have 15 sensors working at the same time properly, and the probability that many of them doesn't work is quite high, as you might be. But it's a good point.
So with that, I think we have to probably go to the break and continue discussions there, but let's thank Carlos again.